Okay, so here's a video for Theorem 12. Theorem 12 is known as dropping a perpendicular. All right, we have given here segment AB and point C, and the idea is to drop a perpendicular. Okay, now, if right angles were allowed instead of compass and straight edge, all you would really have to do is take a piece of paper, line it up with the line, and line up the other edge of the piece of paper with C, and just draw straight down. Because that's really all we need to do for this, is drop a line so that CH will be perpendicular. H would be this point right here. Okay? But again, that's not allowed in geometry. You're not allowed to bring in a right angle instrument of some type and just trace along it. You have to use compass and straight edge. So,
Can't you just do that with your straight edge?
well, because you don't know, you don't have 2 points to line up. You'd have to guess where point H is, and guessing is also strictly forbidden. Okay? So some people will do this like this, and they say, oh, Mr. Blackhawk, I just take my straight edge, and then I line up this edge with the line, and then I make sure this goes through H. That's the same thing as a piece of paper. You are introducing a new tool to the game, which is not allowed. It's like using hands to carry the ball in soccer. You can't do that, okay? It's against the rules. So also you can't use a manufactured right angle in construction. You must only use compass and straight edge, and obviously you cannot use the marks on a straight edge like this. All right, so let's write what's given over here. Given segment AB and C not on it. So C is above the line. It could be below. Then just flip it over and do it the other way. All right. To construct, we need to construct line CH perpendicular. That's what this upside down T means. It means perpendicular to AB. And of course, you know that Euclid's definition of perpendicular is one line standing on another line that makes the adjacent angles equal. So what we'll have to do is after we draw our CH, we'll have to prove that these two angles are equal in order to prove that it's perpendicular. So, step one of the construction is to choose a random point on the other side of AB. Choose, I'm going to call it D. Choose D at random, but it's not just anywhere at random. It has to be on the other side of AB from C, or the opposite side. Okay. On the other side of AB. And by the other side, I mean the other side from C. So I'm just going to choose it right there. There's my D. Okay, and that's not the whole step because I don't need a postulate, theorem, axiom, or definition to choose a point at random. But what I'm going to do with that random point is I'm going to draw circle C with radius CD. And that's a postulate 3. Okay, so here's what that is going to look like. And like Euclid, I am going to go ahead and draw the whole circle, even though mine goes off the paper a little bit. There we go. All right. That created 2 new points. Let's call them E and then Euclid calls the circle itself F, and then he calls this G. So he just says F is like a random point somewhere on that circle. So where the circle, so this is another let here. let the intersection of circle C with line AB be the 2 points G and E. All right. So now, you wouldn't necessarily have to do this in order to make the construction, but we'll need to do this for the proof. And that is, we're going to, well, first we're going to bisect GE. Bisect GE at H. Okay. Do you remember how to bisect GE? What theorem is that? It is theorem not 9, but 10. And so do you remember what it was? All you had to do was, well, yeah, bisect a straight line. How? Didn't we just make a, yes, all we did was make an equilateral triangle on the line. So I'm just going to do that out here. I'm not going to make a big deal out of it. I'm just going to line this up with this. I'm not going to do all the steps. There, we bisected it. Bingo, right there. There's H. So that's all I'm going to do. So that would be theorem 10. All right.
How do we know where F is?
F is just a random point on the circle.
Do we not need to write that down?
No, you don't even have to write that down. All right. Now, really, all we need to do now is draw CH. And we're pretty much done with our construction. But in order to prove it, we're going to need some triangles. So I'm going to say step 3 is draw not only CH, but also CG and CE. And all those are postulate 1. There we go. The construction is finished. I say that CH is perpendicular to AB, but I don't expect you to take my word for it. Given construction as above, I'm going to prove that CH is perpendicular to AB. All right, and do you remember how I said I was going to do it? I was going to prove something about these two angles, right? You're going to prove that they are congruent. And you know by now, I bet you can guess what Euclid is going to tell us about these two triangles. Good. So they could be congruent by the SSS or they could be congruent by the SAS. We have to determine what we can deduce from what's given here. We can't just choose one and just kind of force it into that mold without knowing what we have. Okay? So who can tell me one thing we have between these two triangles that we know for sure? What's one thing, Layla?
Angle C.
Say that again.
Angle C equals angle C.
The problem with saying anything about angle C is that there are 3 angle C's. GCH, ECH, and GCE.
GCE is equal to GCE.
The problem with GCE is that GCE is part of a third triangle that is not congruent to any other triangle in the picture. So, how about Timothy? What do you say?
That line CE is equal to line CG.
Good, let's say that first. CE equals CG. I'm going to mark that with a hash mark on my drawing. And you should be able to tell me why that is. Class, raise your hand if you can tell me why we know for sure that CE is equal to CG. Hey, this is good. I have 5 people. I should have twice as many as 5. Okay. So the question becomes, where did G and E come from in the first place? That's your hint. Where did we get G and E? It looks like it's based on this item right here in my proof. Okay, good. How about Merrick? Very good. CG and CE are radii of circle C. And we just happen to know that all radii are equal. All right. What are two other things in these two triangles, either angles or sides, that we can prove are equal, Che? You are correct. GH is in fact equal to HE. And raise your hand if you can tell me where we can point to support our contention that GH is equal to HE. Layla, I'll give you a chance to redeem yourself.
Step 2 in the construction.
Very good. Step 2 in the construction, GE is bisected at H using Theorem 10. So that's definition of bisection. Or, as my class last year always like to say, def of beast. I don't know why, they just loved whenever we said def of beast in class. All right. And finally, what is the third set of either sides or angles? Emmy?
CH equals CH.
Excellent. CH equals CH because of axiom 4 or reflexive or things that coincide are equal. Click, click, click. So I just heard ka-chunk, a locker open. So what am I going to say for step 4? Very good. I was hoping somebody would ask that. The order of the first three does not matter. Order does not matter on the first three, but you can't say 4 until you've said all 3 of the first 3 steps. What is 4 going to be? Let's try. Nope. Let's try Layla.
Triangle GCH is congruent to triangle ECH.
Perfect. That's exactly right. And class, the reason is?
SSS.
Very good. It's SSS. We proved all 3 sides congruent. And hence, the next step, what we always say once we get the locker open? Yes. And which of the 3 treasures are we going to take out of the locker? Okay, Emmy? Excellent. That's exactly what we said we were going to do. And what does angle 1 equal angle 2 prove to us? Timothy?
That line CH is perpendicular to line AB.
CH perpendicular to AB by definition of perp. Or you can just write the upside down T for perpendicular. And what do we get to say now?
QEF.
QEF, because it's a construction. And there we have it. And so I can stop the video. All right. Be sure to check out our other videos on our channel.